Theorem of perpendicular axis. The moment of inertia of a planar body, that is lamina. Lamina, that means the body which is having the two dimension, about an axis perpendicular to its plane is equal to sum of its moment of inertia about two perpendicular axes concurrent with the perpendicular axis and lying in the plane of the body. The statement is it is very complicated statement, but when I am explaining to you, you can understand it well. According to the statement, the moment of inertia of a planar body, that means we are taking the moment of inertia of this body, and this is the two dimension body which is in the plane x and z. This body is in plane x and z. Okay, now the further statement is about an axis perpendicular to its plane. So because the plane is in xz, so the axis which is perpendicular to this plane is this y-axis. Okay, now to its plane is equal to sum of its moment of inertia about two perpendicular axes concurrent with perpendicular axis and lying in the plane of the body. That means when we are taking out the moment of inertia about y-axis which is perpendicular to the plane of the body, and the two other axes which are in the same plane of this body is x and z. So the moment of inertia about y-axis will be equal to the sum of moment of inertia about x-axis and moment of inertia about z-axis. So the theorem is telling this, if we are taking, means अगर हम लेते हैं इस y-axis के about moment of inertia लेते हैं, तो वो moment of inertia जो है वो सम होना चाहिए moment of inertia x-axis के about और moment of inertia z-axis के about. x और z-axis सेम प्लेन में है जिसमें कि बॉडी है, और y-axis जो है वो बॉडी का जो प्लेन है उसके परपेंडिकुलर एक्सिस है. Okay, so this is the statement. Now we'll understand according to this the moment of inertia about y-axis is equal to moment of inertia about x-axis and plus moment of inertia about z-axis. Okay, now this already I have explained to you that Iy is what? Moment of inertia of the lamina about y-axis, that is Oy. Ix is the moment of inertia of the lamina about Ox, and Iz is the moment of inertia of the lamina about Oz. Okay, now as shown in the figure, you will see that once again as shown in the figure. This is when we are taking the moment of inertia about x-axis. Look at here, about x-axis of this mass. A small mass is there, that is m of this mass. So this mass is z distance, the distance of this mass from the x-axis, the perpendicular distance of this mass from the x-axis is z. So the moment of inertia about x-axis must be mz square. Okay, now you will see that about z-axis if we are taking, so the perpendicular distance from the z-axis of this mass is x. So if we are taking the moment of inertia about z-axis, it must be mx square. Okay, now you will see that this is y-axis and the perpendicular distance of this mass m from y-axis is r. So when we are taking the moment of inertia about y-axis, it must be mr square. So mr square will give us Iy, mz square will give us Ix, and mx square will give us Iz. Okay, understood. Now you will see that this r is perpendicular. If it is x, this much distance is x. Okay, So obviously this will be Z. A triangle is formed here, and you will find that X, Z, R. This will make a rectangle. This will make a triangle, right angle triangle. Okay. So the R square is equal to x square plus z square. That means r will be the hypotenuse. We'll apply the Pythagoras theorem. So it will be r square will be equal to x square plus z square. So same way we have written here the formula, that is r square is equal to x square plus z square. Now we'll multiply mass m in this equation. So it will be mr square, mx square and mz square. Now already we have explained the mr square is what? That is the moment of inertia about y-axis. Mx square is moment of inertia about z-axis. Mz square is moment of inertia about x-axis. Now it is proven that Iy is equal to Iz plus Ix. That means the moment of inertia about a perpendicular axis from the plane of the lamina will be equal to the moment of inertia about sum of the moment of inertia about the axis lying on the plane. Okay. So Iy equal to Ix plus Iz. This is the theorem of perpendicular axis. Now theorem of parallel axis. We'll see the statement first. The moment of inertia of body about any axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through the center of mass or gravity, and the product of its mass and square of the distance between the two parallel axes. This is the statement, and the statement is not very tough. You may understand it. Like the moment of inertia, the statement is given. I'm just explaining the statement first. The moment of inertia of a body about any axis. So we are taking the moment of inertia about this axis AB. It is any axis. Okay. That is AB. And that will be equal to sum of the moment of inertia of the body about a parallel axis passing through the center of mass or gravity. That means the moment of inertia about AB will be equal to sum of the moment of inertia about CM. This CM is the rotational axis that is passing through the center of mass, or if it is a regular body, that means a well-defined regular geometrical shape body. So in such situation, the center of mass and the center of gravity both will coincide. That we have learned already. Okay. So you will consider here that the center of mass or the center of gravity is passing through this point, and the axis is passing through this center of gravity or the center of mass. Okay. So the moment of inertia about AB will be equal to the sum of the moment of inertia about CM and product of its mass and square of the distance between the two parallel axes. Product of its mass, that means the whole mass of the body. Okay. The whole mass of the body, and multiply with the distance, square of the distance between these two. Distance between these two, that means the two parallel axes which we have chosen here. So the that is mass multiplied with d square. D is the distance between these two parallel axes. So mass multiply with d square. Okay. Now according to the theorem of parallel axis, what it is? Moment of inertia about AB will be sum of the moment of inertia about CM plus MD square. Sum of the moment of inertia about CM and MD square. Okay. So once again I am explaining to you the theorem of parallel axis. According to it, moment of inertia AB के about इक्वल होता है moment of inertia cmk about plus md square, where m is the total mass of the body and d is the distance between the two parallel axes which we have chosen, in which one is the any axis about which we are taking the moment of inertia, and another is the axis which is passing through either center of gravity or the center of mass, and most of the time the center of gravity and the center of mass coincide to each other. So we are considering here this cm is passing through the center of mass or the center of gravity. Okay, so IAB, that is the moment of inertia about AB, will be equal to the moment of inertia about cm plus md square, where m is the total mass of the body and d is the perpendicular distance between these two axis AB and CM. Okay, so you might have understand it. Now we are going to prove this theorem. To prove this theorem, let we consider IAB is the moment of inertia of a plane lamina about an axis AB. Okay, and let G, this is the point G, let G be the center of gravity or the mass of the lamina. CM is an axis. CM, this CM is an axis which is parallel to the given axis, AB, and passing through the center of gravity. D is the perpendicular distance between AB and CM, that means the axis AB and the CM. Okay, now m is the mass. Look at here, m is the mass here, which is we have to find out the moment of inertia about this point. Okay, moment of inertia of this point about AB and about CM. Okay, so this is the distance of this particle from the from the rotational axis which is passing through the center of mass or the center of gravity is x, and the total distance of this particle from AB, the axis AB, is x plus d. Okay, so you will see that here when we are taking the moment of inertia, about AB, it must be equal to summation of m, that is it must be equal to what, m, and this will be d plus x square, m d plus x the whole square, because the distance is d plus x, so we are taking the square of the distance, so it would be d plus x the whole square. Okay, now so we have already taken here the moment of inertia about AB must be equal to summation m x plus d the whole square. Now IAB summation m, here x plus d the whole square, will just put the identity a plus b the whole square, which is a square plus b square plus 2ab. So according to that identity we will write here x square plus d square plus 2xd. Now x square will multiply with m will give us summation mx square, d square multiply with m will give us summation md square, and 2dx multiply with m will give us summation 2mxd. Now this is moment of inertia about AB, IAB, that will be equal to, you will see that summation mx square is what? Summation m is actually total m, capital M you can write here. Okay, so this is summation mx square is the ICM, that is the moment of inertia about CM, about axis CM. You will find here, as I explained to you, the distance x here. So mx square, if we are writing summation mx square we are writing, that means the moment of inertia of this body about CM, this axis CM. Okay, now you will see that another quantity came here, that is summation 2mxd. this is summation md square. So summation md square, summation m will give us total mass capital M and d square, and this summation 2mxd another term came, and that will be equal to 0. But why it will be equal to 0? Because you will see that 2mxd, and if we'll write here, this 2 will be came out from the summation, suppose. So summation mxd, summation mx is what? Some here you will see about this lamina, means since the lamina will balance itself about its center of mass or the center of gravity. So the algebraic sum of moment of weight, that means summation mgx, this will be the moment of weight. Okay, so the moments of weight of the constituting particles about the center of mass and the gravity should be 0 because it is balanced. So whatever the positive will take x, that much negative also will come, and that will be cancelled to each other, and that's why this summation mgx will be 0. Now we know that summation mgx, which is called the moment of weight, will be 0 about the center of mass or the center of gravity. Now g, if we'll take out, summation mx will be 0. So if the product of quantities will be 0, so any one quantity must be 0 in that product. So g is not 0 here. G is not 0. What must be 0 then? In such case, summation mx must be 0. And if summation mx must be 0, you will find here in this quantity, summation mx is also present here. So if it is 0, then 0 multiply with 2d, that will give us 0 here. Okay, so this third term will become 0 because we know, we have already know that the weight will be balanced about the means the weight or the mass will be balanced about the center of mass or the center of gravity, and that's why the moment of gravity must be 0. Okay, so that's why this term will be 0. Now you will find IAB is equal to ICM plus MD square, and this is the same thing which we have explained already in the theorem of parallel axis, which state that the moment of inertia about any axis, that is AB, will be equal to sum of the moment of inertia about the center of mass, that is ICM, and the mass multiplied with the square of the distance between the two parallel axes. Okay, that is d square. So IAB is equal to ICM plus MD square, and this is the statement of the theorem of parallel axis which we have proven here. Now moment of inertia of circular ring. We'll see the 4 cases in this. The first case is when we are taking the moment of inertia of circular ring about an axis passing through the center O and perpendicular to the plane of the ring. So for that we have considered here a very thin circular ring. This is, you will see here, and the total mass of this ring is capital M. The radius of the ring is this capital R. Okay, with center O. Now we'll see here, we have chosen an element, a small element here. This is a small element. So first of all, we'll take out the moment of inertia of this small element about this axis which is passing through the center, and we'll extend it or integrate it for the whole length of the ring. So for that, first of all, we'll require the length of the ring. So the length of the ring, obviously it is a thin ring, so the circumference will give you the length of the ring. The circumference will be equal to 2 pi r. So the length of ring is 2 pi r. Now we'll see mass per unit length. mass per unit length, that will be equal to the total mass m upon the total length of the ring, which is 2 pi r. So this is mass per unit length will be equal to m upon 2 pi r. Why we are taking this? Because we have to find out the mass of the element. So we'll see the mass of the element. Mass of the element which we have chosen here, and that will be equal to, this is equal to, you will see that the mass per unit length m upon 2 pi r, m upon 2 pi r, and the length of the element, that is, we'll consider here, this is as dx, so it will be dx. Mass of the element will be m upon 2 pi r multiply with dx. Okay, so this length is there, dx. Now after that we'll see the mass of the element we have taken out. So for the moment of inertia for the element, moment of inertia of this element, moment of inertia of the element will be equal to dm. This is the mass of the element, we'll consider as dm. So this is will be equal to dm, that is the mass of the element, multiply with the distance, perpendicular distance from the center or from the rotational axis. So square of the perpendicular distance from the rotational axis. So I am just writing here, this is perpendicular distance, and we are taking the square of the perpendicular distance. So the mass of the element already we have calculated, that is dm, and dm is what? That is equal to m upon 2 pi r multiply with dx, and here you will see that the perpendicular distance is what? The perpendicular distance is r square of this element. R is the perpendicular distance and square of it is r square. Okay, now if we have to take out the moment of inertia, moment of inertia about axis, about axis, this is passing through center, passing through center. I'm just indicating it with the IC, that is the moment of inertia passing through the center, IC. That will be calculated by integrating the moment of inertia of the element, moment of inertia of this element from 0 to 2 pi r. 0 to 2 pi r, that means from 0 to for whole length of the ring. So the moment of inertia of the whole ring will be calculated about the center, about the axis passing through the center. So we are integrating it from 0 to 2 pi r, and the formula which we have written already, that is dm r square. Dm is the mass of the element and r square is the perpendicular distance here. Okay, so here also I am just writing dm into r square. Okay, now we'll see here, that is IC, which is integrating from 0 to 2 pi r, and the dm already we have calculated, which is m 2 pi r and dx multiply with r square. So what we'll find here, the m is the constant quantity and it will come out. So this will be coming out. 2 pi is also a constant quantity, that also will come out, and the integration here you will find here, that is this r and this r will be cancelled, one r will be cancelled. Now it will be what? It is from 0 to 2 pi r, and will integrate here r, will integrate r dx. Okay, so when we integrate here, r is also a constant quantity, radius is also constant quantity, that will also come out. So simply we'll integrate dx here, and the integration of dx will give us what? It will give us x. And what will be the value of x? The integration of dx is x. The value of x is from 0 to 2 pi r, that is the upper limit is 2 pi r. So we'll put the value mr 2 pi. The upper limit is 2 pi r. So in place of x we'll put 2 pi r, minus the lower limit is 0. So we'll put 0 here, and the quantity will come, that is mr upon 2 pi multiply with 2 pi r. 2 pi would be cancelled, then the quantity will come, that is mr square. mr square, that means the moment of inertia about an axis passing through the center will be equal to IC equal to mr square for a circular ring. So this is IC mr square. This is the first part of the derivation of the formula for the moment of inertia of circular ring. Now we will calculate the moment of inertia of circular ring about one of the diameter. For this we'll use the theorem of perpendicular axis. So you will see that this is an axis which is passing through the center, and we have taken the two diameter here, that is AB and CD, and obviously the ring is the plane of the ring is perpendicular to this axis. So obviously you will see that the two diameter which we have chosen, AB and CD, that will be also perpendicular to this axis which is passing through the center. Okay, now we'll see here, according to theorem of perpendicular axis, we'll see that this is the center. This axis which we have chosen is the IC, that will be equal to IAB plus ICD. Okay, so IC must be equal to IAB and ICD. IAB and CD, AB and CD, these are the two diameters of the circular ring. So I can write here this as ID and ID. Both will be equal then. Okay, so ID and ID. You will find here IC already we have calculated, that is mr square. Previously we have derived the formula for the IC, that means the moment of inertia which is passing through the moment of inertia about an axis which is passing through the center of the ring. Okay, so that is IC, and this will be the formula which we'll put here. IC is mr square. So this may be the 2, means this can be a 2ID. Okay, ID and ID, the moment of inertia, this will be 2ID. Now mr square upon 2, and this is ID. ID is for the moment of inertia about one of the diameter. Okay, so ID is now what? It is mr square upon 2. The moment of inertia about one of the diameter will be equal to mr square upon 2. Now we'll see the moment of inertia of circular ring tangentially parallel to diameter. For this you will see here, this is a ring, okay, and you will find if this is a diameter and this point is the tangent. Here you will see axis which is passing through tangentially through this ring and which is parallel to the diameter. This is the diameter and parallel to the diameter. So we have to find out the moment of inertia about this axis which is passing through tangentially through the ring and parallel to the diameter. So for this we'll see we can apply the theorem of parallel axis, and we know that according to theorem of parallel axis, theorem of parallel axis, the moment of inertia about any axis, that means IKL, this axis I am taking, is equal to the moment of inertia passing through the center. This is the center, okay, that is IAB, here center of mass, plus the whole mass of the body, that is capital M, and square of the distance between these two. So the distance is R, the radius, okay, so square of the distance between these two, that means mr square. So according to theorem of parallel axis, the moment of inertia about axis KL will be equal to sum of moment of inertia about one of the diameter, that is AB, and plus mr square. So IAB is actually diameter here. Okay, AB is actually diameter and IAB is the moment of inertia about one of the diameter. So we can write this ID also, and this is mr square. Okay, now IKL ID already we have calculated in a previous section. You will find that is mr square upon 2. So we'll just put the value of ID, that is mr square upon 2, and this is also plus mr square. Now what you will find, IKL is, this is 2 times mr square if you are taking the LCM. So 2 mr square plus mr square will give us 3 mr square upon 2. Okay, so by adding it, mr square upon 2 plus mr square will find 3 mr square upon 2, and this will be the moment of inertia about an axis which is passing through tangentially parallel to the diameter के parallel है, and because it is parallel to the diameter, I am just changing this sign and I'll write it like this parallel sign so that you may understand very well. This is what, this is about an axis which is passing through parallel to the tangentially parallel to the diameter. Okay, so this is the formula for the moment of inertia of a circular ring about an axis passing tangentially parallel to the diameter. Now the fourth case we will see moment of inertia of a circular ring tangentially perpendicular to diameter. Tangentially perpendicular to diameter, that means suppose this is a ring and this is the diameter, means a line which is passing through the diameter. Okay, so another axis which is passing through this ring tangentially means just touching at one point, but perpendicular to the diameter this way. You can see perpendicular to the diameter in this way. Okay, so this is we have to calculate. Here you will see the circular ring and this is the diameter, and another axis is there which is passing through the center and which is perpendicular to the diameter, and this is the axis about which we have to take out the moment of inertia, and this axis is passing tangentially, touching at one point in the at the ring, and this is perpendicular to the diameter but parallel to the axis which is passing through the center and perpendicular to the diameter, and which we have taken out in the first case. Okay, so here also we can apply the theorem of parallel axis, and now you will see that according to theorem of parallel axis, theorem of parallel axis will find out the moment of inertia about KL, that is IKL will be equal to the moment of inertia passing through the center of this. You can see that the passing through the center. Okay, so IC and the total mass of the ring M and the distance between these two, and distance between these two is also R square, R. Okay, so we'll take R square. Now IKL is equal to IKL, that equal to IC plus MR square. We have already calculated the moment of inertia about an axis passing through the center of the ring and perpendicular to the plane of the ring, that is IC, which we have taken out is what? MR square. So this is also MR square. Now IKL is equal to 2MR square, or you can say I'll just change here. This IKL is actually the moment of inertia about an axis passing through tangentially perpendicular to the diameter. So here I am just writing a perpendicular sign in place of KL. Okay, so moment of inertia, that is equal to 2MR square. So this is the fourth case of the circular ring.